so let us very quickly in next 10 to 15 minutes basically get to know what were the things that happened yesterday. When we talk of segmentation, now there are two addresses that we are talking of. One address is the actual address in the RAM, another address is what the compiler generates. The compiler, when it compiles the code, assumes that your code starts at 0, your data starts at 0, your code segment starts at 0, your data segment starts at 0, and from that point onwards it will assemble your data and the code. So all the addresses generated by your compiler, that is part of your assembly code which is compiled, will be with respect to a 0, right. So that is what we saw in yesterday's class, in the previous sessions. But now what happens further is that every such logical address, that is a logical address because you assume that it starts from a logical 0, and everything with every offset that the compiler generates is with respect to that logical 0. Now that value gets added to a segment base and you get the actual physical RAM address. So there are two addresses we have understood yesterday, one is the physical address, another is the logical address. So the physical address is used to identify each byte of the main memory. The x86 architecture that we are talking of is a byte addressable architecture, and so every memory location, every byte can be addressed individually, right. So since we have 32-bit, we can address 4 gigabytes, right. So for example, a system with 2 GB RAM will have a physical address of 2 GB. The logical address is the address that the programs running on top of the CPU use. They need not be based on the amount of physical memory that the system has. So a 32-bit system has a logical address space of 2 power 32, right. So if you are not using virtual memory, then what will happen? The logical addresses generated by your system plus the segment base should be within the limits of the physical address, because there is no virtual memory given to you, right. Now we know that segmentation provides isolation between different programs. It also provides isolation between the segments. We talked about it in great detail yesterday. So what is memory segmentation? It partitions the addressable memory space into smaller protected address spaces called segments, okay. So we have also introduced a lot amount of protection across these spaces. So a segment, as we saw yesterday, can hold code, can hold data, can hold stack, and there are also some system data structures like TSS and LDT, right, the task state segment and local descriptor tables and your GDT. So the segment can hold all these stuffs. Now this is how a typical memory will look when it is in run. So that what you see here is there are two processes running, one is P1, another is P2. You see P1's code, P1's data, P1 stack, P2's data, P2 stack and P2's code, and then you will have some LDTs and TSS. So this is typically how a segment will look. And very interestingly, the segmentation at x86 does not allow anything, any code or data or stack to overgrow its limit. So whenever there is a overgrowing, like for example your P1's code cannot grow into the space allocated for P2's data, for example here. If that happens, then automatically the architecture will catch you and it says you are trying to do something illegal. So this is the architectural aid that we talked of yesterday. And then coming back to this, there is a, so we had a notion of a segment descriptor. We had a notion that this segment descriptor introduces some amount of privileges, and then these descriptors are stored in the local descriptor and the global descriptor tables, right. So this also we covered yesterday, and this is the whatever you see down here is actually the diagram of a segment descriptor. It describes the content of the segment descriptor. So yesterday we also covered this, right. So there are two, so these descriptors are stored in descriptor tables. There are two segment descriptor tables. One is called the global descriptor table, another is called the local descriptor table. Okay. So the global descriptor table typically is used to hold the kernel data structures, right, and and you can load the global descriptor table at any point by using the global descriptor table register. So in that sense, the global descriptor table is configurable in the sense that it can be loaded at any point in the memory. Now the global descriptor table is called global because it is common to all the processes, and we also covered this in great detail in yesterday's in last set of sessions. Now this is typically how a global descriptor table looks. So a global descriptor table or any descriptor table essentially has code segment descriptors, stack segment descriptors for different processes, and it could have task state segment descriptor. We also understood what task state segment essentially means. It can also have a descriptor to the LDT of a process. So many things can be there inside a GDT, but typically GDT will have the code stack data plus TSS plus LDTs, but that code stack and data would be for only the kernel processes, and for all the local processes all the stack data and code for the local processes will be stored in the corresponding LDTs. Similarly, the LDT is a per process stuff, and so it is given by the the start of the LDT is given by LDTR, right, and the LDT and the GDT themselves will reside in segments, and that will have that will be inside the operating system memory. Those segments would be described for inside the operating system memory. And then we also yesterday discussed when a process is trying to access a segment. So when it is trying to access a segment, it has to load the corresponding segment register. So whether that offset in the segment register, is it pointing to the GDT or LDT, and we did see that there is one bit, there are 3 bits that are wasted. Instead of putting zeros, we use for some constructive purpose, and there is a bit, the second bit, if it is 0 then it is pointing to a GDT, and if it is 1 it is pointing to a LDT. So this also we saw yesterday, right, and so this is just a diagrammatic illustration of what I talked in the previous slide. So if the T1 is 0, then the segment is selected from the global descriptor table. If the T1 is 1, then it is selected from the local descriptor table. And then we also saw that there were 3 bits in this global and local descriptor when we try to address these tables, because all the segment descriptors start at 8 byte boundary. So we had this 3 bits that are actually wasted, and in the 3 bits, 1 bit we used to indicate whether it is GDT or LDT. The remaining 2 bits we used it for what we call as a request star privilege level, right. By using this request star privilege level, I can weaken my privilege. So a higher, so it actually overrides your DPL. You take the maximum of what is given in the DPL and RPL, and so this can be used to actually execute some higher privilege, that means numerically lower privilege code with a higher with a numerically higher privilege level, right. So So, there is the RPL which is also part, which is used when the code is requesting to load the selector. Then we also talked about the segment registers. The segment register has actually points to an offset within the global descriptor table and the local descriptor table, right. And along with the segment register, there is also a hidden part which basically stores the base address, limit and access information of the current segment that particular segment register is pointing to, and this is actually important for performance reasons. So, this is it. So, this is how the, for example, let us say this is the GDT. So, the GDT grows from bottom. So, the bottom 0, actually 0 cannot store anything. So, I want, so please note, see the move statements on the left hand side top, move GS comma 0. So, I want GS to store actually a null descriptor, right. Then move FS comma 0x18, right. So, 0x18 is 16 plus 8 24, which is the third segment. 0th is P1's GS, first is P1's ES, second is P1's LDT and third is P1's FS. So, 0 1 2 3. Please note that FS now actually takes that fourth descriptor from bottom. Similarly, move ES comma 0x08, 0x08 essentially stands for the second, that is the first segment, that is 0 and the first. So, you now see that ES is taking the P1's ES, P1's descriptor, that is the first descriptor from the bottom. Similarly, you can see that SS is taking the 64 plus 8, 72, 72 is 9th descriptor, 0 1 2 3 4 5 6 7 9, right. So, SS is basically taking the SS is taking this 64 plus 8 72, 72 is the 9th descriptor, okay. So, 0 1 2 3 4 5 6 7, I think there is some small error in this slide. So, it is actually SS is taking the 7th descriptor. So, what should be the 7th descriptor? 7 should be 7 8 56, right, because each is 8 bytes. So, the 7th descriptor should be 56, and what is 56? 38, okay. So, it should be 38, 38 is 3 into 16 is 48 plus 8 56. So, move SS comma 0x38, okay. Similarly, we go on and so CS should be 48. So, this is how you load the segment register, and depending on the value that you are loading on the segment register, the corresponding segment in the GDT will be mapped onto, right. So, this is the logical to physical address translation in the absence of virtual memory. So, you have a segment selector, that segment selector will point to a segment descriptor that will give you a base address, to which you add the effective address that is generated by the compiler to actually get the address in the RAM. So, this is how basically segmentation works. So, this is it. So, if your compiled program says ds colon 4 and ds is pointing to 0x20, so the 0x20 descriptor is nothing but we will have base 0x2000 and 0x4 is given here. So, the linear address would be 0x2004. So, this is how you work. We cannot disable segmentation in the protected mode, but what we can do, like many operating system does, is that you just say that the entire 4 GB is one segment. You map the code, stack, everything to one single segment, so that there is no segmentation. So, it is equivalent to saying there is no segmentation. but for protection and security purpose it is not advisable to do for all the things that we have seen so far. So, there a best preference would be to have a multi-segment model. So, here you see here there are many segments that are loaded, and some of the active segments are selected using the segment registers and they are currently active, and when they become inactive somebody else becomes active, the corresponding segment register will be updated with that offset. So, currently if you see the first 1, 2, 3, 4, 5, 6 are active. So, what you see on the leftmost side is the segment registers, what you see on the middle is the segment descriptor, and what you see on the right hand side is your physical memory. Now, all the segment registers are mapped onto one segment here, segment descriptor here, and so the first 6 segment descriptors are currently active. Suppose the third descriptor which DS is pointing to becomes inactive and you want some other to be the DS, you just make that DS point to this, right. So, I could have multiple amount of segment descriptors in my local descriptor or the global descriptor table, but some of them will actually be mapped, some which are really active will be mapped onto the corresponding segment registers. And these are the types of user level descriptors. We said there are 2 types of descriptors, the system descriptor and the user descriptors. So, these are the 16 types of user descriptors that we have seen yesterday. So, the top 8 are basically data descriptors and the bottom 8 are code descriptors. And then this is just a very quick summary of what happened, what we discussed yesterday. So, each descriptor can there could be a privilege level for each descriptor. So, if your source code is at privilege 0, it can access a destination segment or a destination code or data segment which is at privilege 3 directly, but it cannot go and read a destination code even though it is in privilege 3, but it is execute only, I will not be in a position to read it, right. So, I have a privilege 0 source code, it can jump to a destination code at privilege 3, but it can't go and read the destination code segment which is execute only even though it is privilege 3, right. Similarly, source code at privilege 3 cannot jump or read a destination code or data at which has a DPL of privilege 0. Similarly, a source code at privilege 0 can read or write at privilege 3, but cannot write into a data segment which is at privilege 3, which a read only data segment at privilege 3. A source code at privilege 3 cannot read or write any data in privilege 0. So, for the less privileged code, so we introduced a notion of call gate through which a code can access a lesser privileged numerically lesser privileged code. So, a source code in privilege 1 using a gate can go and access a interrupt service routine or any code at privilege 0 using the call gate or the trap gate, right. So, these are, so just I will quickly go through again. A source code at privilege 0 can jump to a destination code at privilege 3, a pros code at privilege 0 cannot jump to a destination code at privilege 3 if that cannot read a destination code segment at privilege 3 if it is a execute only segment. Similarly, a source code at privilege 3 cannot jump to a destination code at a lesser privilege. A source code at privilege 0 can read or write any data into a data segment at privilege 3 or above privilege 0, and similarly but it cannot write into a data segment which is read only even though the privilege is higher, numerically higher. A source code at privilege 3 cannot access, cannot read or nor write into a data segment visit at privilege 0. But a source code at any privilege can go and access something at a privilege level lesser than that using the notion of call gates and interrupt gates. We have already seen this. Now, all these gates, are they insecure? If you actually have some if you actually have if you are not careful about coding, then it is a problem. So, this is one case study. Gurung is actually a worm that installs actually a call gate so that it can get higher privilege, because in some earlier versions of Windows the GDT was not protected. So, it went and installed a call gate there, and once I install a call gate, I can do whatever I want. I can get my privilege escalations very quickly. If I can go and define what the call gate is, that call gate descriptor, then I can do wonders. Please understand that it is a major vulnerability. Now, this is all about segmentation. This is a very quick summary about segmentation, and now what we will try and do, I will answer some questions immediately, and then we will go into the assignment part. We will start looking at the assignment, and hopefully many of you or all of you can run that assignment in your place and see that it is all working.